Alright, so we've talked about exponential functions. Now let's talk about logarithmic functions. And just like with exponential functions, we need to start by choosing a base to work with. So that's how we would begin. So we'll start by fixing some number a. It's some real number that is positive, but also not equal to 1. We're going to be a little bit more specific than we were in the case of exponential functions. Now, this is the notation that you would use to write down a logarithmic function. So I'll just draw your attention over here. F of x, that's just the letter that I'm using to define a function. There's no need to actually use the letter f here. You could use any letter you like, but here, this is the notation for a log. So we write log, that's short for logarithm. Then you write the base as a subscript immediately after. And then afterwards, you specify the number that you want to plug into the logarithmic function. So this log base a of x means we want to plug the number x into the logarithmic function of base a. Now, notice I haven't really told you what it means exactly or how to compute it. All I'm telling you at this point is what this function is called. So it's called the logarithmic function with base a. Okay, so let's start with the name. Now, how do you evaluate it? How do you actually work out what log base a of some number x actually is? Like if I plug in a particular number x, how do I work out what this evaluates to? And I think the best way to think about it is this. Think of this notation here, log base a of x. Think of it as asking a question. And here's the question that it's asking. What exponent would I have to place on the number a in order to make the power evaluate to the number x? Now, sometimes that question will have an answer and sometimes it won't. And for values of x for which it does have an answer, well, then this notation just evaluates to exactly what that answer is. Okay, so that's how I think about what logs are. Let me write that down in the form of a note underneath, because it helps to actually see this written out in front of us. Right, so here's what we do. We'll write log base a of the number x is equal to some number y. So now we're going to write out exactly what it means for this to be true. So log base a of x is equal to some number y if and only if. This is the if and only if symbol, by the way. It's just an arrow pointing in two directions. In mathematics, if you put it between two logical statements, you're saying that the two statements are equivalent and that they're true in the exact same circumstances. So what statement's going to go over here? Well, really just the one I just said. Here's how you check if this is true. If someone comes to you and says that they've computed log base a of some number x and they've gotten the answer of y, the way you check if they're correct is you just take this number a, whatever the base was, raise it to the power of y, and check if they actually get x. And if that's the case, that means this y is the answer to the question that log base a of x asks, and therefore it evaluates to y. So the rule you use to check is just check if a to the power of y is equal to x. So this really defines what it means for log base a of x to be y. It's true if and only if this statement is true. And since we already understand exponential functions and we understand exponents, this statement is straightforward to check. So by making this statement equivalent to this statement, in doing so you're providing a definition for the logarithmic function. Let me just write down one last comment about this symbol. This is the first time I've used it, but I will use it again in this course. So this means if and only if. Right, just a reminder, if you see that between two mathematical statements, it means that both statements are equivalent. Okay, so let me now do a couple of examples, because this has all been abstract so far, so it's a little easier to think about this if you actually have a couple of examples to look at. So first one I'm going to do, let's use some numbers. How about log base 2? So 2 is a positive number and it's not equal to 1, so 2 is a perfectly valid base. And then we'll plug in the number 16. So log base 2 of 16. Remember, this is asking a question. What exponent would I have to place on the number 2 in order to get 16 back as the result? And actually the answer is 4. So this evaluates to 4. So if you wanted to give a reason, you could say because. Essentially just check the corresponding exponential statement, right? Just check that 2 to the power of 4 actually gives you the number 16, which is plugged into the log. And of course it does. You can check that that's true. So because 2 to the power of 4 is equal to 16, that's why this statement is true. So that's an example of one log. Another example, if I had log base 4 of the number 1, how would I evaluate that? And remember, you're asking a question. You're saying, what exponent would I have to place on the number 4 to get 1 back as the answer? And it turns out, in this case, this log is going to evaluate to 0. Because if I raise 4 to the power of 0, I get 1. In fact, anything raised to the power of 0 would give me 1. Okay, so let me add a couple of remarks here. There's some space over on the page. I'm just going to add them over here. The first remark is that the domain of any logarithmic function, so if I take log base a of x, this is going to be defined for all values of x which are positive. So that actually tells you what the domain is for a log. So I'll write it this way. I'll say the domain of log base a is equal to the set of all positive numbers. So I can write that as an interval, right? The set of all positive numbers, I'll just write it as an open interval with no upper bound. I'm not including 0 because 0 is not in the domain of a log. Really, what does it mean for, why is it that the domain of a log function is all positive numbers? Well, remember that this notation asks a question, and this notation is hence going to be defined exactly when that question has a unique answer. And it just turns out it's going to have a unique answer exactly when the number x is a positive real number. So that is why the domain of any logarithmic function with any base at all, as long as it's a positive number not equal to 1, the domain is going to be all positive real numbers. So that's the first remark. The second remark is actually a generalization of the second example here. We said log base 4 of 1 is equal to 0, and there's nothing special about 4 here, right? If anything to the power of 0 is equal to 1, so actually you can state something more general here. No matter what your base a is, log base a of 1 is always going to be 0. Okay, and let's say that these remarks hold for any base a. So for any positive a not equal to 1. These remarks are valid, right? That this is true for any base a, this is true for any base a, and there's one more actually we can write down. What if I actually plug the base of a log into the log? So what if I actually took log base a and then I plugged in a? What would I get in this case? And it turns out you're going to get the same thing no matter what the base a is. And to answer the question of what this evaluates to, just remember, this notation asks the following question. What power do I have to raise this number to in order to get this number back as a result? And of course, if I take a to the power of 1, I'm going to get a back. So the answer is, in this case, 1. So that actually works no matter what the base a is. So if you plug 1 into any log, the result is always 0. If you plug the base of any log into itself, the result is always 1. So those are just a couple of properties. Some pieces of notation that are useful. Two bases that we commonly take are 10 and the exponential constant e. So in general, this is going to happen more in other courses probably than this one, but if you're in the physical sciences, you'll probably use log base 10 quite often. So sometimes you just won't even specify that you're working in log base 10. You'll just write the word log. So if you see that, it doesn't mean you don't have a base. It just means that you're taking your base a to be equal to 10. So this is equal to log base 10. If you don't specify the log base, it's automatically taken to be 10. So this, by the way, this notation here, I think this might be the first time I've used this one as well. This looks like an equals sign, but you can see there's a colon immediately to the left, these two dots. All that means is that this it's kind of like an equation, except it's providing a definition. So when we write something like this, what we're saying is that this notation actually literally means this. So we're not just saying that these two things are equal. We're saying that this is actually the definition of this. Let's actually write that down as a comment too. This is another piece of notation that's going to come up a lot in this course, and you might see it in other courses as well. So this means is defined as or is defined to be. Either is fine, right? So that's what that notation means. Another common base that you'll use is the exponential constant, and that's actually the one that we'll use in this course, and that's called the natural log. So in fact, we just use ln as an abbreviation for it. So that's the natural log, and this is defined to be also a log. but with base taken to be the exponential constant e. So let's add a few more words in here. So log base 10, this is called the common logarithm. And the natural log, our log base e, is called the natural logarithm. All right, so those are worth underlining. Okay, what about the graphs? We did graphs for exponential functions. We can talk about the graphs of logarithmic functions as well. And again, we're going to consider two different cases. We're going to consider the first case will be when a is greater than 1, and the other case is just going to be when a is less than 1. We don't have a third case where a is equal to 1 because we've actually ruled that out this time. So that's why we only have 2 pictures here instead of 3 pictures like we did in the exponential function. Okay, so in the case where a is greater than 1, well, the function is always going to go through the x-axis, or the graph is always going to go through the x-axis at the point x equals 1. And then as the x values increase, the graph of this function goes upward and it kind of arcs over to the right. But it still grows arbitrarily high. It doesn't like curve over and hit an asymptote or get bounded at any point. If you draw any horizontal line, this curve will eventually punch through it, no matter how high you draw the horizontal line. And then as the values of x move to the left, remember our domain is only the positive numbers x. So we're only going to draw a picture on the right-hand side of the y-axis. But as you move closer to the y-axis, the curve just gets closer and closer to the y-axis. So the y-axis is a vertical asymptote for the logarithmic function with base a. So that's if a is greater than 1. The other case you can consider is if a is less than 1, but still, of course, greater than 0, because remember, a has to be greater than 0. So in case 2, you can consider the case where a is strictly between 0 and 1. And just like with the graphs of the exponential function, if you move from a base a that's greater than 1 to a base a that's less than 1, you kind of just invert the picture. Right? You're still going to go through the point 1 on the x-axis. I'll label it right there. It's going to arc over to the right. And it has the same property. If I draw any horizontal line, no matter how low I go along the y-axis, if I draw a horizontal line that cuts through the y-axis, this curve will eventually punch through it. So it goes down arbitrarily low, but it does arc over to the right. And then, again, the y-axis is a vertical asymptote. So as the x values get closer and closer to 0, you approach the y-axis asymptotically, but just in the other direction. It's in the vertical direction this time. Okay, so those are what the graphs of logs look like. And then now we'll finish this discussion with just a few properties of logarithms. Really, these properties are what logs are really made for. So these are really powerful properties. And then we'll do some examples, more examples on the next page. So we've got some positive number a that's not equal to 1. We're starting with that in the background again, just a reminder. That's just so that a is a suitable base for a logarithm. And the following 3 properties are true for any positive numbers x and y. Why do we insist that x and y are positive? Just so that they're in the domain of the log, right? Because remember, the domain of the log, of any log, is all positive numbers. Okay, so let's write these properties down. The first one, if you were to say it in ordinary language, you could say that logs turn multiplication into addition, which is actually a powerful thing to do if you think about it, because multiplication is a more complicated operation than addition. So if you can turn multiplication into addition, you're making something simpler. But what does that even mean? What does it mean to say a function turns multiplication into addition? Here's what it means in the case of logs. If I take log base a of a product, so 2 numbers x and y that are multiplied together first, and then the product is plugged into the log, here's an alternative way to compute that. I can take log base a of x, and I could take log base a of y separately, but then add the results. And that's what it means for logs to turn, because here I have multiplication, but if I want to take the logs of the individual factors and put them together afterwards, I can do that, but I'd put them together with addition. So that's what it means to say that logs turn multiplication into addition. The second condition, or not condition, property of logs, it's very similar to this one, but just with subtraction. If I take the log of a quotient, so log base a of the quotient x divided by y, Well, logs turn division, because that's what a fraction really is, it's division, into subtraction. So it's going to look a lot like this, except subtraction in the middle. I can take log base a of x, and then take log base a of y, and then I put those two calculations together with subtraction, and that will give me the same as if I took log base a of the fraction x over y directly. Okay, so one last property. This is my favorite one. It says the following: if you have the log base a of a power, so let's say x is the base and y is the exponent, so log base a of x raised to the power of y, this property says that you can actually take this power right out of the log, and you can just bring it right down in front of the log and multiply it on instead. So that's actually really powerful, because exponentiation, if you will, is a really is the more complicated than any of the arithmetic operations. It gets complex really quickly depending on what the exponent is. So the fact that you can now rewrite this as y times log base a of x is actually really powerful, because this is a lot more straightforward. If this is log base a of just x is simpler than log base a of x raised to the power of y. And yeah, of course, you have to multiply the y on after, but just multiplying by y is a lot simpler than raising something to the power of y. So that's the application of the power of this property. Okay, so those are a few properties of logs. We'll look at some ways to use logs on the next page.